Hello everyone, this is Zhongcheng Ma from Hamilton University of Applied Sciences speaking. I'm the Principal Research Scientist at Ham Tech Research Unit. The title of my presentation is Structure-File Analysis of One-Story Steel-Framed Building with Steel Cladding. This presentation is divided into 5 main sessions: introductions, firm modeling of steel cladding, firm model of the building, structure response, and conclusion. This is a one-story industry steel-framed building with steel claddings. Typically in Finland, the sandwich panels are used as wall cladding and trapezoidal sheeting plus insulation as roof cladding. The system is subjected to vertical snow load and horizontal wind load. The research questions are: in case of fire, are there stabilization effects for individual members against buckling and the entire building against wind and catenary actions from snow loads? We answer the first research questions in another presentation in this conference and the second question in this presentation. The RFCS project consists of 9 work packages. Work packages 2 to 4 are the testing part, and 5 to 6 are the firm simulation part. Work package 5 is regarding the simulation of the tests, and work package 6 is the simulation of the entire building, which including the stabilization of individual members at elevated temperature and entire building in fire. Task 4 is regarding the stabilization of the entire building in fire. The result will be present in this presentation. This slide shows the non-partners in this project. Temple University of Technology, now Temple University, is a coordinator, and HAMC is the work package leader of work package 6. Now let's move to section 2, firm modeling of steel cladding. The building includes sandwich panels, wall, and trapezoidal roof sheeting. The computational resource will be too intensive if 3-dimensional shear and solid elements are used for the roof sheet and sandwich panels. Therefore, simplification must be made. In airplane industry, equivalent orthotropic plates has been used to replace the trapezoidal sheets in system-level modeling. Both extensional stiffness and the bending stiffness are in equivalence. For sandwich panel in 5 compartment, due to glue melting and delamination of inner steel face in fire, we can either ignore the panel contribution or model the panel as 2 layers of composite shear by ignoring the inner face. For cool compartment, the 3 layers composite shear element with soft core are used. Next, we will go to the finite element model of the one-story industrial building. Upper picture shows the structure frame with traditional wind bracing, and the lower picture shows a building frame with steel claddings. The steel column is HEA 600 and rafter is HEA 500. Struts and bracing element are tubular sections. Snow load on roof is 2 kN per square meter, and wind load is applied on the frame. This slide shows the elastic plastic spring property for short nails and self-drilling screw connectors. The temperature-dependent force displacement curve are taken from the work by Lu et al. 2012 for short nails and Ward et al. 2018 for self-drilling screws. These are the temperature history of steel elements based on 2D or 3D temperature analysis at ISO standard 5. They are used as an input for structure file analysis. Next, we will go to the structure responses session. There are two types of stabilization, in fact, discussed here in case of phi. The first one is to resist the horizontal wind load in case of phi. The second is to resist the horizontal force due to cantilever action of the roof and the snow load. This video is from the computer simulation in case of ISO standard phi in 3 bays. The first runaway occurred when the temperature of rafter is around 400 to 500 degrees due to material softening. Then the cantilever action are developed in the roof system and the struts to hold the vertical load. The frame in both sides of the phi compartment start to resist the tension force in the roof strut. Meanwhile, the compression force are developed in the edge strut. With the heating time, the edge struts are softened and the buckling finally occur, which results in the final collapse of the entire building. Top left graph illustrates the vertical displacement in the middle of the roof in the phi compartment. Two-stage runway can be seen. Lower left graph shows the actual force development in the strut. It can be seen that the actual force developed to around 250 kilonewton after first runway. Top right graph corresponding the horizontal displacement in the sidemost two frames. The dark curves in these graphs are for the case without sandwich panel in the phi compartment, and the green curves are for the cases with two-layer composite shell for the panels in the phi compartment. These slides include two cases. The brown curves are the case of traditional wind bracing system, and dark curves are the case for the frame with steel claddings. This slide shows the response for phi and snow load case. It can be seen that the case with the steel cladding gave longer phi resistance than the traditional bracing case. This slide shows phi with both wind load and snow load. In this case, the traditional bracing structure gave longer phi resistance than steel cladding only. However, the wind load plus snow load case is not controlling case. The snow load case is most unfavorable case. There are several failure criteria according to deformational responses available at this moment, mostly based on the safety in the phi test facilities. The time corresponding to failure is defined either by first mid-span displacement of L divided by 20, where L is the span length, or second, deflection rate of L squared divided by 900D, where D is the cross-section height, or 3, deflection of L squared divided by 400D. Based on this research, criteria deflection of L squared divided by 400D is close to the final collapse of the building. Now let's go to the conclusion session. Based on the study in this paper, we found that around 22% increase in the fire resistance with a studied cladding system than the traditional bracing system in fire plus the snow load case. Around 8% decrease in wind snow load case. However, this is not a controlling case. The stabilization on the horizontal force due to the cantilever action is significant in the cool compartment wall by centimeter panel cladding. The financial support from IFCS STEP-FAE research project and FESFS research project by Finnish Fire Protection Fund are greatly acknowledged. This is a reference. Thank you for your attention.